My name is Elizabeth DeBenedictis, and this is slime. Slime is a naturally occurring material. We can see it sticking to rocks, it's in a wet environment, and it's gross. Some slime contains communities of bacteria, and the slime helps the bacteria survive in harsh environments, stick to surfaces, and spread. These are actually called biofilms. As a mechanical engineer, I'm interested in studying slime and biofilms. And over the next 7 minutes, I'm going to tell you why they're an important topic to study and why we might even want to make more of them. To the first point of why would we want to study slime, we could just generalize this to why would we study a natural material? There are plenty of valid answers to this question, but as an engineer, my answer would be because nature can help us design better materials. One very famous example of this is of the lotus leaf. Humans have long understood that lotus leaves repel water, but it wasn't until experimental techniques evolved enough for us to be able to zoom in very far to look at the surface of the lotus leaf to see that it's this rough geometry that makes the water want to ball up and roll off instead of spread out on the surface. Once we understand this principle, we can then apply it to man-made materials like water-resistant clothing. So naturally, my next question is, can we apply the same design process to slime? Before we start making all kinds of slimy materials, we first need to understand what it is about slime that we want to copy. Here are a couple of places where slime tends to show up: in naval and industrial applications, on medical devices, or in the plaque on your teeth. One common theme here is it tends to stick in places where we really don't want it, and it tends to attach strongly. If we think about this for a moment, we'll realize that slime can stick to many different types of surfaces, and it's difficult to remove. These are both qualities that are important for an adhesive. And also the fact that these are mostly in or near wet environments means that we could use these principles to develop underwater adhesives. So now our question is, can we use slime to develop better adhesives? We already know that it sticks strongly. And kind of like the lotus leaf, we want to look in closely to see what enables slime to adhere. If we look up close, we can see bacteria with all these hair-like fibers. Through experiments, we know that these fibers are important for adhesion, and some of these fibers are called Curli. These are the fibers that I'm personally very interested in. But right now, we don't really understand exactly what it is about Curli that helps the slime adhere. We don't know, for example, if it's features like the chemistry or the shape, or just the fact that there's a lot of them. Because we don't understand this, we can't use these principles to design better adhesives or other materials. And you might suggest, well, maybe we should just zoom in again and look up really closely at the Curli. But unfortunately, Curli are difficult to see in detail. There are some inherent properties of the structure that make it difficult to see Curli on length scales where it's very easy to see other materials. So now we're kind of stuck, and we need to think about if we're approaching this problem the right way. We need to ask ourselves, what other methods can we use to learn how slime sticks? Mostly so far, I've just talked about using experiments to look really closely at materials to understand how they work. But in fact, experiment and computation together can help us understand the world around us better. For example, you could experimentally observe a phenomena, use theory and simulation to understand the underlying physics, and then test this again using experiment. For example, experiments have already revealed some important aspects of the Curli growth. We know that they grow on the surface of bacteria. We know that they're made out of these building blocks. We know the weight of these building blocks, but we don't exactly know the shape, so they're just represented by cylinders here. Because we don't really fully understand the structure, we can't understand the mechanics in detail, and we can't apply this to new materials. And this is where I come in, because I'm a computational researcher, and I'm very interested in Curli. Luckily, computer simulations can help us fill in some of the gaps from experiment. Using what we already know, we can generate computational models of the building block and the fibers that they form, and try and use these to better understand the mechanics of the Curli fiber. But computation isn't just useful for creating models. You can actually run little experiments within your computer to better understand the mechanics of a system. So for example, we'd be interested in looking at fiber adhesion to a surface and in determining what features are critical for this, whether it be things like the chemistry or the geometry. Once we understand this, then we can apply these techniques to man-made materials. But it turns out Curli are useful for more than just understanding adhesion. Remember earlier how I said we might even want to make more slime? Well, Curli have a number of features that are advantageous in just creating any type of new biomaterial. They're modular, so they have these little discrete building blocks. They self-assemble, they're strong, and they can be mutated. The last one is huge. Now we can mutate these building blocks with all different types of modifications or mutations, and they'll still maintain their same structure and strength and self-assemble just into a material with different properties. So now we can look at designing these very rationally in order to achieve specific material properties that we want. Initially, we were just asking, can slime help us design better adhesives? And now we're using the principles of Curli to help design better underwater adhesives. But in fact, along the way, we've learned that we can do much more with Curli. We can take these fibers, apply all sorts of functionalizations, and create new biomaterials. For example, some that are used with Curli would be custom gels with tunable mechanical properties, sponges to help remove contaminants from our environment, or microbial nanowires for conduction in small bioelectronics. So in sum, using experimental insights and computational approach, we can engineer Curli to help build a better slime. Thank you.